Here are 4 more triple integral problems for you to try. Give them a try. Pause the video, give them a try, and then I'll have solutions with a few comments for you. I like to start with the drawing, but when there are too many planes and things and they're intersecting, often it gets too messy, so I just kind of indicated things. So this is a region bound by a number of planes. So we start with z equals 0, so that's the xy plane here. So just know that you're going to stop at the xy plane, nothing underneath. And then you go up to z equals pi. So I kind of indicated that. So this is where things are going to stop in the height direction. Y equals 0, that's kind of this back wall here. And then y equals 1. Y equals 0, I'm sorry, y equals 0 will be this wall here along the x-axis. And then y equals 1 is another kind of wall that is at this line, but it kind of, parallels the x-axis. We have x equals 0, so that's this back wall. And then we also have this plane. So this given to us by the equation x plus y equals 1. And I did rewrite that as y equals 1 minus x, so I could write that line here. So I plotted the line, so when x is 0, y is equal to 1. When x is 1, y is equal to 0. So I have my line plotted here, but just realize that it goes all the way up. And also it's a plane, so it's tilted and most likely hits the z-axis. So then I'm ready to set my limits of integration. And I do have this horrible affliction where I like to always write my variables in order of x, y, z. I feel like it's easier for me to see the height, z, so that's always on the outside. But sometimes it doesn't work out that way, and sometimes you need a different change of variables. But this is what I naturally try first, and if it's not working out well, I can't get my limits of integration well, then I might try something different. But here, as I said, I look at this and I see z. It's very plainly going, from 0 up to pi. And then y, so y, remember, can only depend on the variable z. But in this case, z really doesn't depend on x and y. So really, you're just concerned about how x and y depend on each other. So in this case, y can go from 0 to 1. You can specify y going from 0 to 1 because y has no dependence on z. And what keeps this from being a square domain, which this is not because of this plane here, the y equals 1 minus x plane, is you set your x limits. And your x limits is going to be set according to this plane. So x goes from here, the origin, all the way out to this line. At this point, it's going from the origin all the way out to the line 1 minus y. So this is how I set up my limits, and the rest is just integrating and plugging in. For this next problem, we have a region bound by the cylinder z equals y squared, which actually does not look like a cylinder. It looks a lot like a parabola. And then the solid it forms looks like a bowl, like a fruit bowl, to me anyway, but we'll look at it. And the plane's x equals 0, so x is equal to 0. So this back, is that where x equals 0? Yes, this back wall here. And then at x equals 1, there's another wall. So think of kind of over here at x equals 1, there's another wall perpendicular to this back wall. And then we have y equals -2 and z equals 2. So I see why they call this a cylinder, because it's not the interior of this cylinder. It's not the bowl we're looking at. It's kind of this cylinder with some area cut out. So anyway, looking at our limits of integration. I had told you in the previous video about my affliction of wanting to favor integral order of integration as being dx, dy, dz. But in this case, I look at this, and both x and y, they're not dependent on any variable. So it makes sense to have one of those two, x or y, on the outside, and I chose x. So I guess I decided if I couldn't do dx, dy, dz, I would go in the opposite direction. So x and y, again, their limits are set here. It's like a rectangle. Well, it is a rectangle, not even like a rectangle. It is a rectangle. So the only thing that really depends on something else is z. And this is also, I'm going to draw this. Z goes from the xy plane and this curve. So it goes from the xy plane, z equals 0, up to the curve. This is also kind of what told me that this was not, we were not doing a volume of the interior. It's these two things here, the cylinder and the xy plane. And so then you set your limits of integration for z to be 0 up to the curve y squared. And you're done. And it doesn't matter which one is next, x or y. It can be dz, dx, dy. It's just as easy as dz, dy, dx. And you can give it a try if you just want to verify for yourself. So this next problem is to find the volume of the solid bound by this paraboloid, z equals 4x squared plus y squared, and the cylinder y squared plus z equals 2, which, if you solve this, is z equals 2 minus y squared. You can plot some points to see that you have this kind of shape, or you can also see for the level curve, so like when z is equal to 0, you have the single point at the origin, and then when z is equal to, say, 4 squared, essentially you have this ellipse. Well, basically the form of this equation is of an ellipse, and as z gets higher, the ellipse gets bigger, so you have this bowl shape here. As for the cylinder, if you look at this form, z equals 2 minus y squared, so you know y squared is a parabola, but the negative is what flips it upside down, and then the 2 moves it from the upside down from the origin up to z equals 2, so it kind of raises it up. So then we're looking for the volume within this space here. So again, I have this preference to have x on the outside, z on the inside, and in this case this works out because z goes exactly from this lower paraboloid cylinder up to this paraboloid, right? So z is going from one curve up to the next curve. So I have the lower cylinder, and at the top I have the paraboloid. So that works out really well. And actually, I know I said I did dz because that's my preference, but also just looking at the picture, these are the two functions that's easy to solve for. Now I need to know how y depends on x. So if I look at this, there's a circle here, but that's going to be a little bit too big because actually the circle that the x and y are dependent on each other, it's not from here to here, it's only from here to here. So it's a much smaller circle. So what I did is I set these two equations equal, the paraboloid and the cylinder over here. And then I got the relation that y is equal to the square root of 1 minus 2x squared. And it's sort of a ellipse, so it's a plus and minus. So this is what sets my limits of integration when I integrate in terms of y. Last, to determine my limits on x, is I look at this, and when I set y equals to 0, I see that x goes from negative 1 square root of 2 to 1 square root of 2. So this is how I set up this integral, triple integral. This last problem, I have this horrible drawing. I'm sorry about it, but I'll explain it to you. So change the order of integration of this integral here, negative 1 to 1, y squared to 1, 0 to 1 minus x, f of x, yz, dz, dx, dy. So I'm going to look at this and I say z goes from 0, so it's from the xy plane, up to this equation of a plane. So we should recognize this as an equation of a plane. Next, we have our relation between x and y. So we have a relation of x equals y squared. So that's a parabola in the xy plane. So I drew this parabola here in the xy plane when z is equal to 0. And I see that x is going from this parabola up to x equals 1. So from this parabola up to x equals 1. Here's the line x equals 1. So from this curve to x equals 1, or the edge of this curve until they meet over here. And where do they meet? They meet at y equals negative 1 to 1. And you can plug in the point x equals 1, and that's this point here. You can plug in x equals minus 1 here, and that gives you this point here. Here is our last problem, and it's to switch the order of integration of this integral, negative 1 to 1, y squared to 1, 0 to 1 minus x, and this is the equation of a plane, which you should recognize. The function fxyz, dz, dx, dy. So there are 3 variables, and so there are 6 different ways to arrange 3 variables. So this is 1, and these are the other 5 possible changes of order. I'm going to do 1 in detail. On the next slide, I have the answers for the other 4. And so let's go ahead and get started. So first I have this really terrible drawing, which I have to apologize for. This is probably a better one. It's from the other page, so I like this more. We'll work with this one. Anyway, so if we look at this, we have the relation of z. Z goes from 0, the xy plane. So maybe we'll use this here, where it goes from 0, xy plane, up to the plane 1 minus x. And actually the intersection of the plane, or not the intersection, but the part of the plane that's over the parabola is essentially this kind of shape over here that I have. I'll just shade it in yellow, because essentially the plane over the parabola kind of gives it that parabola shape. So again, 0 is going from the xy axis up to the top of the plane, the xy axis to the top of the plane. I guess here it goes all the way up here. That's that limit of integration. The next limit of integration gives you the relation of x and y. In particular, x is equal to y squared. So that's where we get this paraboloid here. So when 0 is equal to 0, we have this relation between x and y. So we have a parabola. And then last we have y going from -1 to 1. So I tried to put those limits of integration in blue here for y. So here's our first order of integration. Now, this one, I'm just going to switch y and x. That should be pretty easy. I'll leave z as it is. And then, actually, let me draw this out for you once before I start this one. So when we look at the domain, when we go from x going from 1 to y squared and y going from -1 to 1, so we're in this area, and x is going from y squared to 1. So I'm just going to trace that out. If x goes from y squared, that's this curve, to 1, it's going to go from the curve up to 1, only between y equals -1 and 1. So it's this area in green. So when we set up our limits of integration here, we still want this area in green. If I look at this now, I can have x go between 0 and 1, because that's actually the values for x. It goes from the origin up to 1. Then y, solving over here, it's going to go from this side of the parabola, the left side of the parabola, to the right side of the parabola. In other words, y is going to be the square root, solving the equation algebraically, square root of x, from the negative square root to the positive square root. And so again, I'm going to shade this in green. So for x going from, oops, that was not green. For x going from 0 to 1, y is going to go from this side of the parabola, the left side of the parabola, to the right side of the parabola. So you can see I'm going to get the same domain. So this is my solution when my order of integration is dz, dy, dx. So here are my 5 solutions. I did 1 on the previous page, and it occurred to me I should do at least 1 where we change the order of z. So I'm going to do this middle one here. If I have z at the end, I need to know the range of z. But I do know that z is equal to 1 minus x. And then I also know, which I wrote down here, z is equal to 1 minus x. And I also know that x is equal to y squared. So I rewrote z is equal to 1 minus y squared. Y ranges between -1 and 1. So this is going to be maximized at 0. So that, when y is equal to 0. So that means z ranges from values of 0 up to 1. So this point here, that's where I got this. Next, I have my variable x, which I need to write in terms of z. But actually, that's not too hard, because we literally have z is equal to 1 minus x. So solving for x is going to go from 0 to 1 minus z. And then last, I have y, but we also have y in terms of x. It's going to go from negative square root of x to square root of x. So this is how I get this. I'll leave it to you to verify solutions for the other 3. And that's it for this video. Thank you for watching.